This is my presentation on the alternatives to attaining optimal model complexity. This is in addition to hyperparameter tuning and regularization. Now, in the machine learning field, the performance of a model is heavily dependent on the quality of the data that is supplied to it. There are situations when the model performance is impacted even after supplying good data by either bias or variance. We go into the definitions of bias and variance. Bias can be described as the difference between the actual prediction of our model to the correct value we are trying to be predicted. Examples of low bias machine learning algorithms are decision trees, k-nearest neighbor, support vector machines, and those that are and the models that are high bias machine learning algorithms include linear regression, discriminant analysis, and logistic regression. Definition of variance is it is a complete opposite of bias. In this case, during training, the created model is allowed to inspect and search data for a certain number of times to find a pattern in it. If it cannot work properly on the data for a long enough time, it will not find patterns and bias occurs. An example of a low variance machine learning algorithms include linear regression, linear discriminant analysis, and logistic regression. And those for high variance machine learning algorithms include decision trees, k-nearest neighbors, and support vector machines. The high bias and high variance problem. One of the other ways of calling high bias and high variance are underfitting and overfitting. But to rectify this, when we modify a machine learning algorithm to better fit a given dataset, it will either turn to lead to low bias, but will also increase the variance. And this way the model will fit with the data, but also while increasing the chances of inaccurate predictions. The same applies while creating a low variance model with a higher bias. Although it will reduce the risk of inaccurate predictions, the model will not properly match the dataset. And we have some diagrams showing overfitting, underfitting, and a good balance. These are the ways that we can attain optimal model complexity. One way to tackle high variance will be to train the data using multiple models. One of the approaches is ensemble learning methods, which helps to leverage both weak and strong learners in a model to improve the model prediction. Now, in the second approach would be in the presence of an imbalanced dataset, where we can use weighted or penalized models to be an alternative. And then we'll have to increase the data so that the data to noise ratio will be higher, which will also help reduce variance in the model. Now, to fix continuation of fixing high variance, in addition to providing extra data, we can also use data augmentation techniques to modify, crop existing data to also fix the high variance. Another approach would be to go for smaller sets of features, which also would fix the high variance problem. The applications here would be finding out correlation and the relationships between the input and target variables. To fix the issue of high bias, would have to add more features that can help fix the bias. This would involve feature engineering, such as going through the iterative approach of deriving new features or modifying the ones basing on the requirements of the analysis. Another approach would be adding polynomial features, which allows to fit higher order equations and which fixes a higher bias. Now, higher order polynomials fit the training data extremely well and the test data extremely poorly. Now, this will have a low bias on the training data but a very high variance. Steps to find the right polynomial equation are as below. You'd have to create a list of possible low to high degree polynomial equations, learn the coefficients from the training set, which would be 70% of the data for each polynomial degree, while finding the training error. And finally, you find the polynomial degree with the least error using the validation set. One other way to treat bias and variance is to achieve model generalization, and this is done by decreasing the lambda, which fixes a high bias, and also increasing lambda, which fixes high variance. And the description goes as to say that to regularize the parameter, as the regularization parameter increases, the model fit becomes more rigid. And on the other hand, as lambda approaches 0, the model tends to fit the data. Now the question is to decide what is the appropriate value of lambda. And the procedure is below. You have to create a list of lambda values, starting with 0 as you increase by a given margin, which is in this case 0.02. So you create a set of models with the different degrees, and you continue to iterate as you compute the validation error, and then that gives you coefficients that you can use to compute the lambda. And in the end, you select the best combination that produces the lowest error on the validation set. And with that, I conclude and thank you very much. This is my submission.